This is the problem-solving session of Lecture 10 on composition of functions. If you've been systematically looking at these videos from the beginning and you have not looked further ahead for later lectures, you may be surprised by certain changes. This is the second board. What happened was I finished, well, I thought I'd finished all the lectures for this course, so right up to lecture 19, and I then systematically looked at all the clips, all the video clips I sent up to YouTube to see if, just systematic search, see if something was wrong. And there was one clip missing, and the clip that was missing is what this one's being recorded at now, which was the problem solving for lecture 10. So I will, to be systematic, not leave a gap, I'll fill it in now. So there are 5 questions at the end of chapter 10 in the textbook. So I'll do 2 of them. Question 1, which is about injection and surjection, and question 4, which is 5 true or false type questions. Barnard really likes true and false. Alright, question 1. I've written it up here a bit. So you're given 2 functions. F maps a set A into set B, and another function G maps B back into A, so maps B to A. And you're also told, so you're given these 2 things, but you're also told that there's a composite function. You perform F first. Remember, usually the function on the right is the one that's applied first. So you apply F first and then G. And when you do that, you get the identity function for set A, I of A here, right? And the question is, you're to show 2 things. That this F is injective, so F is an injection, and you also have to show that G is surjective, that this is surjective. Okay, well, let's do the first one. Show that F is injective. What does injective mean? Injective. That means that every element in, so we're talking about A, right? We have to show that F is injective. So we're going from set A to set B. So we're going from left to right. We're going this way. So to show that F is injective, that means that every element in B is mapped to at most once. In other words, each element could be mapped once or not at all, right? That's injective. And how do you prove that a mapping, a function, is injective? The typical method, you let two elements in your B, in your codomain, be equal. So let's say 2 elements in A, and X and Y. So X maps to F of X here, and let's say Y maps to F of Y here. So let's assume that these 2, F of X equals F of Y, and then we have to show that X equals Y. Because if X and Y are different, then you've got 2 points mapping to the same value, F of X. If F of Y equals F of X, these two points are effectively the same point. So, but if X and Y are different, then you've got a 2-to-1 mapping. And by definition, that is not injective. Right? Injective is at most 1 element in A, the domain, maps to it. Alright? Okay, so assume these 2 are equal, so F of X equals F of Y, but we can use this, right? So let's just pre-multiply both sides by G. So now we've got GF of X equals GF of Y. But GF is what? Well, it's just the identity function, IA. So rewrite GF as just IA, hence IY. Now x and y both belong to set A, so this is the identity function on elements of A. So IA of x is just x. That's what the identity function does. It doesn't change anything. So IA of x is x, IA of y is y. So we've shown that these two are equal. So if f of x equals f of y, then x equals y, and that's your proof that your function f is injective. Right? Therefore, f is injective. Okay, so we've done that part. Now, second part, you're asked to show that G is surjective. Sur is French for on, right? So it's an onto mapping. And what does surjective mean? Done this many times, but a bit of revision. Surjective, an onto mapping. What does that mean? It means now we're asked to say that G is surjective. Now G goes from B to A, back to A. So this G mapping is going this way, right, from right to left. That may be a bit confusing because we're used to talking about surjective when we go from left to right, but this time it's the other way. So be aware, a bit confusing. All right, so we're asked to show that G is injective. So what does that mean? It means every element in your codomain. Now here the codomain is A, right? Because we're going B back to A. So we're starting with B. G acts on elements of B, maps them into elements of A. So in this context, set B is now the domain, the starting set, right? And A is the codomain or the target set, right? So we're going this way, right to left. All right. So for G to be surjective, what does that mean? It means every element in your codomain, your target set, gets mapped to. At least once. At least once. That's the definition of surjective. So that means for any element belonging to A, let's call it X. So for any X belonging to A, there's an element in B that maps to it. Right? Remember surjective? Every element in your codomain has to be mapped to. There has to be an arrow coming to that element in your codomain's Venn diagram, right? So for every element here, there has to be some element in your domain that maps to it. So for any x in your codomain, there's an element in your domain, your starting set, which in this case is B. We're starting here and mapping that way, right? So that G maps that element. Let's call it W, right? So there is some element W in your domain. W belongs to B. So that G maps that element W into your element X. So G of W equals X. Okay, I hope you follow that. If not, rewind. Okay. So we're trying to show for any X here, there's some element W in domain that gets mapped to X. Right? Let's call it W. Right. So G maps that W into X, and we have to show that this W exists. Right? We have to find what W is that allows this to be possible. So that G of W equals X. We have to use this information. We don't have any other information. So let's use something like this. Right, we've got a G here, and we know GF is I. So we want a GF maybe. So we've got a GF. So let W be f of something, right? if W is f of something, then we'll have GF of something. And we know what GF is, it's I. And we want to the result to be X. Well, that's a strong clue, so let your W be just f of X. And where'd that come from? Well, if you substitute W by f of X, so instead of W, now put f of X here, well, you then get GF of X. GF. The GF is the identity in set A, right? So we get GF of X. Well, that's the identity function of X, which is just X. Great. Okay, we found it, right? If we choose W to be just f of X, that will work, right? G of f of X gives you X. So for any X here, the corresponding element in your domain will just be f of X. Okay? Alright, so that's done. Right now some true and false questions. Some fairly easy, some not so. Alright, so there are 5 of them. True or false? And I've written some of it up, not all, as a visual guide. True or false? The inverse of FG, and then I'm just